Okay, can you tell me what are the story stiffnesses? All story stiffnesses are same, so that is, just now you told 179, what is it?
14.92.
Story stiffnesses, that is one, not one,
179. 179.125.
179.12. Okay, and story mass, so it is, how much it is? 106 something, you said.
Yes, sir. 106.2.
106.2.
Yes, sir.
Okay, and then here 150 something, 158
158.
point
865.
point
865.
865 or 87. Okay, and what about this 97 something?
97.64.
64. Okay. So change these values in your code as well. These are the story stiffnesses and masses. Now using this, if you suppose write differential equation and then write down the matrix, the K matrix will be this, the M matrix will be diagonal like this, and if you solve the eigenvalue problem, now actually you have to you should not use the EIE command to solve the eigenvalue problem. Actual case, what you should be doing is, actually this will be very large matrices, so you will solve using some of the numerical methods that we have discussed earlier. But in this class I am going to directly use EIG k, comma M, this command, and this command gives me all the mode shapes and natural frequencies square lambda values. So from this I calculate omega and t values here, and then once that is done, then I have to calculate seismic weights. So I have told you how to calculate seismic weight. Once we have masses, then seismic weights. So seismic weight for story 1 is equal to mass of story 1 into g, acceleration due to gravity, plus some percentage of imposed load. So let us calculate that. Mass m1 is equal to 106,207 into 9.81 plus percentage of imposed load. So what is the imposed load on first story? Imposed load everywhere is 3.5, and if 3.5, how much percentage I should take here?
50%.
50% of the total imposed load. So 50% of what is the total imposed load here? 3500 Newton into cross sectional area. The area entire, this one is 9 into 8. So how much it is?
11.67 into 10 to the power 5.
11.67 into 10 to the power 5. You should tell me the units.
Newton.
W2. Similarly, m2 into g plus percentage of imposed load, 50% of this, which is also equal to, now in this case, w3 equal to so on.
Please explain 9 into 8.
Huh? How much? What?
That 9 into 8. In infill ball.
I'm not getting. What is the
Sir,
value?
Sir, I'm asking that 9 into 8. Please explain that. About
This
0.5
one.
into
9.8 kg.
9 into 8.
So he's talking about area, sir.
Okay, this
Area.
area. See, imposed load is 3.5 kilonewton per meter square, isn't it? So that is 3500 Newton per meter square. So per meter square of the slab you have 3500. So total, what is the total area of the slab? This is 9 meter into 8 meter, isn't it?
Yes, sir. Okay.
So that is 9 into 8. Tell me what is this answer here? (16 point or 15 point something?
16.85 into 10 power 5.
16.85 10 to the power 5 Newton, and W10 is equal to
10
remember
10.84 into 10 power 5.
in this case you should not consider any imposed load,
Okay, sir. Okay, sir.
only M10 into G.
Okay, sir. Okay, sir.
What is it?
Zero point 0.97 10 to the power of 5.
0.97
10 to the power of 5.
10 to the power 5 Newton. Okay, so much smaller. Anyway, so now
Sir, 9.57 into 10 to the power.
that
Yes, sir. 9.
that I think is reasonable. It is much smaller than that. 9.75, isn't it?
No, sir. 9.57.
57.
57. 57.
9.58.
Okay, 9.57 10 to the power 5 Newton. So that seems to be correct value. These are seismic weights. So let us substitute these values here. Sorry, tell me the values once again. No, I have actually written here code here. So it is just 9. Okay. So we have all the W10 values, and then based on that I have calculated W matrix. Just like mass matrix, we have seismic weight matrix, which is diagonal from W1 to W10. And then just for the sake of finding out what is the total seismic weight, I have calculated this sum of all the weights W1 to W10. Up to this, complete the code and let us execute this code. Once we execute this code, we can have mass matrix, which is our diagonal matrix, stiffness matrix, tri-diagonal, and phi, which is our mode shape. Then we have omega, which are our natural frequencies. We have T, fundamental periods, natural periods, and we have W, that is weight matrix. So that is also diagonal, you can see that clearly. Okay, so and W total seismic weight. So all these quantities are obtained. Now let us go to IS code and see what IS code tells us about the next steps. Let us go to page number 24. Yeah, here. So what we have done is we have found out natural modes of oscillation. Oops. Yes. So we have found out natural modes of oscillation, natural frequencies and mode shapes. So this part is done. Now number of modes to be considered. What this code tells me about number of modes to be considered. I should consider modes such that modal masses should be at least 90% of the total seismic mass, and from here onwards I started making mistake. The first mistake was that I very often do, and that is giving expression for modal mass. So last time I told you the expression for modal mass was like phi transpose m1 by phi transpose m5. The modal mass expression is here. this entire section I have forgot actually. The modal mass expression is given here, and it is same as what I said earlier, only with one small difference. I forgot this square. So this is nothing but phi transpose or phi k. For kth mode it is phi k transpose. Instead of mass you can take weight as well, seismic weights. W 1, so this is unit, and square of this, I forgot this, divided by phi k transpose W phi k, and then this G. Since I am not using mass, I am using weight here, so that's why this has to be divided by G. Or you can use seismic masses also here, that's not a problem. So the expression I told yesterday, that is still valid, but the only difference is I forgot this square. So you can use that, or you can use this expression, both are okay. So now this W is matrix which is n cross n, phi k transpose, that is, let us say this is first modal mass. If I want to find out, then it will be phi 1 transpose, so this will be 1 by 10, this will be 10 by 10, and this will be 10 by 1. So this will be one value, square of that divided by one value. So find out what is the first modal mass in octave using this expression or this expression. Find out what is the first modal mass. We already have phi. The first column of this phi is what we are interested in. And of course we also have weight matrix. Let me write it down here. Phi, order of first column, so that is phi 1 transpose is the prime into weight into ones. So ones is a special command in octave which gives vector of ones, but what is the size of that vector? In this case here it should be 10 cross 1, so 10 rows 1 column. This entire square divided by phi transpose, that is first one, into W into phi. So phi transpose W1 square divided by phi transpose W phi, and I forgot G here because I am using seismic weight, G into, okay. And now let us see how much it is. M1. So this is M1. Understood how to get it? 1.3754 10 to the power 6. So where is it? So modal masses Mk is equal to phi transpose W phi k transpose W 1 whole square divided by phi k transpose G into phi k transpose W phi k. So based on this expression, M1 I have found out, which is equal to 1.3754 10 to the power 6, 1.3754 into 10 to the power 6 kg. Find out M2. Anybody found out M2?
Sir, copy the above expression and make change, sir.
Huh?
1 to 2. Copy the above M1 expression and make change in that.
Copy M1 expression and
Sir, M2 is Sir, M2 is 1.36 into 10 to the power 5.
1.36 10 to the power 6. Let us
Five I'm
check.
getting.
Let us check that. So here I will check this for now. Second 5, and in 3 places I have to change that. M2 1.42 10 to the power 5. That is my answer. Anybody is having different answer over here? So 1.43.
Yes, sir.
Different answer.
Sir, power is correct, but I'm getting 1.36.
So somewhere masses are different then.
Oh, yes, sir, I'm checking it.
Anyway, just check that. 1.43 10 to the power 5. That's the answer that we will accept now. 1.43 into
Yes,
10,
it's 1.43. It's coming.
10 to the power 5 kg. So similarly, you can find out all, but remember, as I said, the system will be very big, like 10 by 10, even more, 100 by 100 or anything, something like that may also be there. So we usually do not calculate all the modal masses and all the natural frequencies, mode shapes and so on. We need only like first few, such that the total modal mass up to that mode is 90% of the total seismic weight, total seismic mass. So we have, for each calculation of modal mass, we have to check whether we have crossed 90% or not. So let us first take total here, total seismic mass. So total seismic mass is equal to, let us say, MT, that is equal to WT divided by 9.81. So seismic weight we have calculated total, that divided by 9.81. So that is equal to, just please tell me what is it. WT we have total, that divided by 9.81, and let us call this as MT. 1.59 10 to the power 6. So this is 1.59 into 10 to the power 6 kg. Okay, so now what we have to do is 90% of this. So 0.9 times MT is equal to, how much it is? 1.4314 10 to the power 6. 1.43 into 10 to the power 6 kg. So I need to take modal masses only up to that, such that it will cross 90% of this value. So now if I take only first modal mass, that is 1.37 10 to the power 6 kg, is it crossing 90% of modal mass?
No, sir.
It's not, isn't it? What if I take M2 as well? So M1 plus M2, is it crossing this mass? Let us do here M1. Okay, M2.
Yes, sir, it will. I think.
Yes, sir, it's crossing, sir.
It's crossing, isn't it? M1 we have this, and M2. So M1 plus M2 is equal to 1.52 10 to the power 6. M1 plus M2 equal to 1.53 into 10 to the power 6 kg. This is more than this. So now that's enough. As per the IS code recommendation, I can stop at mode 2 itself. I need not even calculate other modes, isn't it? So now I'm going to stop. So therefore, only 2 modes are sufficient, since this is more than 0.9 times MT seismic total mass. Okay, so now we have only 2 modes, and that's our conclusion, that is enough for us. Now we decided how many number of modes to be considered using modal masses, and modal masses are given here. Now what we have to do is just follow the same thing, this entire section. As I said, I mentioned that I forgot the simplified method of dynamic analysis. We started with this A part, just follow it with remaining part, that is B, C, D and so on. So this tells me the B part is find out now mode participation factor, and this mode participation factor is given by this. Or again, I always like to use matrix notation, because that is, I feel, easier to remember. This can be written as phi k transpose W1 divided by phi k transpose W phi k. So what's the difference here in these two? Earlier it was just this part was squared and then G divided by G. So in this case the square is not there and divided by G is also not there. You will get mode participation factors Pk. So please find out what are the Pk values. So participation factors. Pk is equal to phi k transpose W1 divided by phi k transpose W phi k. So therefore P1 is equal to, can you tell me, have you found, anybody found out P1? (1133.2). 1133.2. And what should be the unit here? What should be the unit?
So it's unitless.
Unitless, correct. And what about P2? Find out what is P2 value and tell me.
So 364.86.
364.8. Let's just check. Okay. So we have P1, P2. I don't need more participation factors because that's more than enough for us. Only 2 modes need to be considered. Now go ahead and see the next one, that is B part is done. Now design lateral force at each floor in each mode. So peak lateral force QIK at floor I in mode K is given by this expression q I k a k, so on and so forth. So here ak is nothing but the design horizontal acceleration spectrum value, that is ah, that we know how to find out, that I explained in equivalent static method as well. So this ah we have to find out. Pk is already found out, phi is known and wi's are known. So therefore let us use this now. First find out ah values. So the next step would be design, what is this, seismic horizontal coefficient, horizontal acceleration coefficient. Okay. Coefficient, so that is nothing but ah values. So since we have different t values period, for each period we will get one ah value we will call ah1 ah2 and so on for first mode, second mode. So for t is equal to, now what are the values of t? First two values only we need because that's our interest, 1.21 and 0.40. so 1.21, that is t1, and for t2 I will write here 0.40 second. So now for t1 equal to 1.21, find out ah1, which is nothing but sa1 by twice rg. Find out. Z is zone factor. So what is the zone? How will you find out the zone?
So 4.
Zone 4, because the location is given as Roorkee. So for Roorkee, the IS code, if you go to IS code page number
36.
what's the page number?
After 36.
Yeah, actually on page number 11 you will find map 11 or 12 I think, and from that map you can see, or somewhere around end you will find this table here. So this is the table where you can see Roorkee, and then zone is 4 and zone factor is 0.24. So use that. Then this is, let us assume that this is a residential building. So importance factor will be 1. What should be R?
We can take here.
Huh?
5.
Yeah, we have to take 5. You cannot design, I told that, you cannot design ordinary moment resistant frame here. It is section 4, zone 4. So you must have special moment resisting frame. So this has to be 5. And then SA by G. SA by G, you know the expression for 1.21, and assume that what kind of strata Roorkee has, I don't know actually. Let us assume hard rock itself. What is AH1?
0.0198.
What is it?
0.0198. AH1.
0.0198. Okay, and AH2? I don't know these values, so just check. Everybody should confirm that. AH2 for 0.4.
AH1 is same, sir. 0.019.
Okay, AH2.
Correct.
Point 058.
0.058. Is this correct? Whatever. Only SA by G is going to change, nothing else. So AH1, AH2 you have. So from this we have to calculate design lateral force at each floor. So QIK, the expression is QIK is equal to AK phi IK PK WI. So now K corresponds to mode here, and I corresponds to story. So first story, second story, third story, and so on. So I think the time is over. We will continue with this in the next class. Okay. Any doubt here?
Sir, please repeat I again. What type of building have we considered for I?
For I, this
Yeah.
this is index.
Commercial or
You are talking about this part.
Importance factor, sir.
Yes, sir. I. The value of I.
Okay,
So
okay.
what
Importance
building have
factor.
we-
Importance factor. This is a residential building.
Okay, so that will be 1.
And still, I don't think the occupancy is going to be more than 100, so it will be 1.
Okay, sir. Yes.
Anything else?
No.
Okay, so we will continue with this in the next lecture maybe. Okay.